Intuition Uncovered, investing for your future.
So now the following video is going to cover buffers. We're going to look at definitions of buffers, how you make buffers, calculations of the pH of those buffers. We're going to utilize Ka and Kw in those pH calculations of buffers, expressions for buffers and how to explain their use using those expressions, so the system of ions inside those buffers and how they contribute to the action of the buffer, and of course some examples of biological buffers. So a buffer solution, something that resists major changes in pH with the addition of a certain amount of acid or base. Keep in mind, earlier than A levels, you may be used to a buffer simply being a solution that doesn't change the pH or stops the pH changing when you add acids or bases. We've advanced that definition for a reason now. Firstly, when you add acid or base, there are some very slight changes in pH, so a buffer's preventing major changes in pH occurring. The more and more of the acid or base you add, eventually the buffer would be used up, so therefore we have to put into the definition a certain amount of acid or base. So, a buffer solution resists major changes in pH with the addition of a certain amount of acid or base. Let's use methanoic acid as an example. If we had just a beaker of methanoic acid, we know most of this doesn't dissociate, so there's a large concentration of the methanoic acid particles. There are some of the methanoate ions and the H plus ions. They have a very low concentration because this is a weak acid. It partially dissociates, as we've said in the earlier lectures. Now, when you add a weak acid to its own salt or to a solution of its own anion, so if you have a solution of a salt, the salt, such as here, sodium methanoate, would split into methanoate ions and sodium ions. Big concentrations of those in a beaker of sodium methanoate aqueous. Sodium ions are not important. What's important is the large concentration of methanoate ions. The methanoic acid beaker, as we've already said, would have a large concentration of the methanoic acid particles. Put the two together, would end up with a buffer which contains loads of these methanoic acid and loads of these methanoate ions, as I'm showing you down here. The equilibrium is just the way I've represented it at the top. There are sodium ions floating around. I've not included those because they're irrelevant, they're spectators. What's happening now, in the buffer we still have a lot of the methanoic acid particles. These molecules came from the weak acid. We have a lot of these methanoate ions now, which came from our salt solution of the weak acid. And of course there are still H pluses floating around. Methanoate ions and H pluses are no longer equal in terms of their concentration. What we have here at the pure weak acid beaker is an equal amount, an equal concentration of the anion, the A minus, or the methanoate in this case, and the H pluses. They're going to be equal, and that's what helped us to calculate pHs of weak acids, when we knew these two were equal. But in a buffer solution, they are not equal, and that's going to be key for our calculation, which I'll show you an example of now. So a buffer is created by adding 0.1 moles per decimeter cubed solution of methanoic acid to a solution of sodium methanoate, which has a concentration of 0.7 moles per decimeter cubed. Calculate the pH of this solution, and of course this is now a buffer solution. The Ka for methanoic acid is 1.8 times 10 to the minus 4 moles per decimeter cubed. So pause the video here, have a go for yourself, and then you can see how I've dealt with this question. So my answers. Now, firstly, let's remind ourselves the Ka expression, the dissociation of methanoic acid brings us this. We can now remind ourselves as well, this is not applicable in this sense because in a buffer solution, the H plus and the A minus, or the methanoate ions in this case, are not equal. So we cannot simplify this to H plus squared. So ignore that now. In a buffer solution, we stick to this expression. Let's plug the numbers in. There's the Ka. The concentration of my methanoate ions is 0.7, and that came from my sodium methanoate solution, reminding ourselves the sodium methanoate split into the sodium ions and the methanoate ions completely. So whatever the concentration of sodium methanoate, 0.7, is also the concentration of the methanoate ions. Likewise for methanoic acid, assuming most of them are still methanoic acid, very few have dissociated, we keep 0.1 moles per decimeter cubed as the concentration and we put that down at the bottom. The only thing left is H+. Rearranging all of that gives us this expression, and here's a concentration of H+. Now, putting that into pH equals minus log to the base 10 of H plus concentration gives us a pH of 4.6 to 1 decimal place. Now furthermore, calculate the pH of the solution when 0.02 moles of sodium hydroxide are added to 500 centimeters cubed of this buffer solution. Now, this is another way buffers are going to be tested at a more advanced level. Not only must you calculate the pH of the buffer itself, but then if you were to practically add either an acid or a base, and they may give you a solution, or maybe even the actual moles, you must then know the technique of how to calculate the new pH of the buffer. So, I'll give you a moment, pause the video, and I'll show you my answers. And so my answers. And this gives me an opportunity to talk about how the buffer is going to work. So, we have a solution, a beaker, with lots of these methanoic acids, the weak acid floating around. We've got loads of the anions, the conjugate base of that acid, so in this case the methanoate ions floating around. If we were to add acid, so basically some hydrogen ions, we increase the concentration of H+. According to Le Chatelier's principle, the position of equilibrium will shift to oppose the change placed upon it. So in this equilibrium here, adding H+, the position of equilibrium would shift to the left, using up some of those methanoate ions, making more of the methanoic acid. Because we have loads of these methanoate ions floating around, we know that enough of them are around to catch those H pluses and form methanoic acid. Likewise, if you add a base, so for instance adding hydroxide ions, they would then react with these H pluses and remove them from the solution. And again, with Le Chatelier's principle, we can appreciate the methanoic acid molecules with loads of those floating around could then dissociate and replace the H pluses that are being removed because we're adding a base. And of course, more of these methanoate ions would be created as well. In this case, we were adding sodium hydroxide. It's a strong base, so we're effectively adding 0.02 moles of the hydroxide ions. They're going to use up some of those H pluses. Well, how many of them are there? Well, let's have a look. In 500 centimeters cubed, before adding a sodium hydroxide, I know the concentrations of my methanoate ions and methanoic acid. Back to the question, 0.1 moles per decimeter cubed methanoic acid, 0.7 moles per decimeter cubed for the sodium methanoate, therefore methanoate ions. I can use that on the volume 500 to calculate how many moles of methanoic acid are floating in that 500 centimeters cubed of buffer solution, and of course 0.35 moles of the methanoate ions floating in that buffer originally. Now, if we go ahead and add 0.02 moles of the sodium hydroxide, these hydroxide ions will use up some of the H pluses that are around, and to replace them, methanoic acid will have to replace those H pluses and dissociate. Therefore, I can take away the moles of 0.02 of those hydroxide ions from the methanoic acid that were floating around. That gives me 0.03 of the methanoic acid still left. 0.02 were used to replace those H pluses that were being used up. I can also calculate the concentration of my methanoic acid now in 500 centimeters cubed. Go back to your AS chemistry and remind yourself of how you would do that using the CV over 1000 equals moles. Here again, methanoate ions, 0.7 times 500 over 1000 gave me the original moles. I've now added, because OH minus ions were being added, they've gone and caused more of these methanoic acid molecules to dissociate. I have now created 0.02 moles of these methanoate ions, because I've added 0.02 moles of OH minus. They use up the H pluses. 0.02 moles of the methanoic acid dissociated. I've created 0.02 moles of the methanoate ions. My new moles of methanoate ions is 0.37, the concentration 0.74. Now, plug these concentrations back into our original equation. That's the Ka for methanoic acid. Methanoate ion concentration 0.06 is the concentration of methanoic acid. H plus is the unknown. Rearrange things to give us that as the concentration of H plus, and our new pH is 4.8. What I hope you now appreciate is adding some base, we expected the pH to slightly go up, and it has ever so slightly gone up. I added a whole pile of sodium hydroxide ions, but the buffer was able to resist major changes in pH, i.e. prevented the pH rising too drastically, went up by 0.2 only. In the Q&A video, I go through a variety of examples on how the examiner may test these, and a variety of examples of how buffers can potentially be difficult questions, but once you've had a chance to practice them in the exam, are a source of many marks and hopefully enough to get you the grade you want. So, in the blood, the pH needs to be carefully regulated between 7.35 and 7.45. This is done in the plasma part of the blood. Now, what's going to happen is carbonic anhydrase, which is found inside red blood cells, takes the CO2 which you're making from respiration, a chemical reaction inside all living cells. As you burn the energy, such as glucose, in the presence of oxygen, you produce water and CO2. The water and the CO2 become hydrogen carbonate. And when you react these two together to give you the hydrogen carbonate, the plasma and the blood cells have a lot of these hydrogen carbonate ions also present, and together the pair of these can form the buffer solution. So, this buffer system, if you were to then add more hydrogen ions, something acidic, the hydrogen carbonate ions can take the excess H pluses, according to Le Chatelier's principles, and shift the position of equilibrium to the left, making more of these carbonic acids. And if you have these hydroxide ions being added, some sort of a base, it can use up the H pluses, and to replace them there's sufficient amount of carbonic acid that can dissociate and give you hydrogen carbonate and the hydrogen ions. So the same principle we've seen previously with methanoic acid we can still apply here to the carbonic acid hydrogen carbonate buffer system in the blood. Towards the lungs, the same can take the carbonic acid, convert it back to CO2 and of course H2O as well, and the CO2 can then be breathed out. So, the buffer system in the blood cannot fall below 7.35 or above 7.45, otherwise it starts to cause denaturation of enzymes and proteins, such as receptors and ion channels. In order to prevent such damage, which can be catastrophic, the blood system has this buffer system here, and describing this is very useful for the exams. We'll look at some questions on this, of course, in the Q&A.
Tuition Uncovered. Investing for your future.